The next paper is called Fast Local Laplacian Filters, Theory and Applications. It's by Mathieu Aubry, Sylvain Paris, Sam Hassanoff, Jan Kautz, and Fredo Durand.
Thanks for the introduction. So today I'm going to speak to you about local Laplacian filters. And the first thing you may ask is why? Well, here is a typical picture. It looks good, but it's also a bit flat. That's why being able to do strong detail enhancement is important. Unfortunately, if you do it in a naive way, a lot of problem appears, especially halos around strong edges. That's why there has been a lot of work on edge-aware image processing for image editing. And today, I'm going to focus on a set of filters that was developed by some of my co-authors, local Laplacian filters. They have the specificity that they don't create any artifact like halos or gradient inversion, even for really extreme transformations like this one. And for this reason, they are really exciting. So there is a lot to like about those filters, but they also have some limitations. Right now, they are too slow. We don't fully understand their theory, and they don't have many applications yet. In my talk, I will address those 3 points. I will make them fast, I will explain how they work, and I will show how we can use them to transfer the gradient statistics from one image to another. These 3 contributions will also be the structure of my talk. But before going into them, I must first explain to you how local Laplacian filters work. Just to be sure we are on the same page, a Gaussian pyramid is a set of images which divide by 2 the resolution at each level. And the Laplacian pyramid is the difference between the successive levels of a Gaussian pyramid. The local Laplacian filters define an output image by defining its Laplacian pyramid. Each coefficient in the Laplacian pyramid depends on a different region in the image. So the idea of local Laplacian filters is to define for each region a locally processed image, relying on a simple intensity remapping. How is this remapping defined? Well, we begin by considering the average of an input region. This average will be the reference for the remapping. Around it, we use, for example, a function that locally decreases the contrast. Look how the curve flattens the intensities around the average. We apply this remapping to the full region, resulting in a smoother image. The pixels, which intensity in the input image was close to the average, have an almost constant value in the output. On the contrary, the rest of the image is almost unchanged. Note that this remapping really depends on the average value, and thus will be different for each region. So now, we know how to process the image locally given a region. And we can compute the Laplacian pyramid corresponding to this processed region. Then, we just copy the corresponding value to the output Laplacian pyramid. And we repeat the same process for each coefficient in the pyramid, each coefficient defining a different region and thus a different remapping. Since one has to compute a remapped region and a pyramid per coefficient, that makes, of course, the local Laplacian filters in their original version slow to compute. Finally, once each output coefficient has been computed, the Laplacian pyramid is collapsed to get the output image. Let's look at the final results of local Laplacian filters. So here is an input image. And here is the image smoothed with the local Laplacian filter using a contrast decreasing function shown on the top right. If we use a contrast increasing function instead, shown in the top right corner again, the results will now be an artifact-free enhanced image, where we can really see the power of local Laplacian filters. All that was in the 2011 paper of my colleagues. But as I mentioned earlier, the local Laplacian filters are very slow to compute, and our first contribution that I will present now is to speed them up. To do that, let's begin by looking at a simplified version of the local Laplacian filters, where only one level is processed. We can understand it as 2 main steps. First, a nonlinear intensity remapping. In the corresponding equation, the G is a reference value for the remapping function. Second, the pyramid construction and processing. And the second step is linear. Using the equation for those two parts, and after some simplification for which I refer you to the paper, we obtain this equation for this simplified one-level local Laplacian filter. This is an important equation which gives the value of the output image at a pixel p as a perturbation over its value in the original image, IP. This perturbation is a sum on a local neighborhood of the influence of nearby image values. This influence is a function of the intensity difference with the neighbor pixels, and it is weighted by a Gaussian weight. So now, using this equation, we can understand better why local Laplacian filters are slow to compute. They are slow because D is spatially varying. One must compute this remapping for each pixel and on its full neighborhood. So at the end, the computational time is proportional to the product of the two. So to make local Laplacian filters fast, everything is about computing D efficiently. If the reference G to consider were constant, we will need to compute the remapping only once, and everything will be fast. So what we did is that we developed this very simple idea and show in the paper that one can approximate the results well by computing the remapping only for a small set of reference values and interpolating. This allows to compute the remapping only for a constant number of time for each pixel, which means approximately 2 orders of magnitude less than before. In practice, one begins by sampling the reference values. Each reference value is associated with a different remapping function. Using those remapping functions, we compute the remapping of the full image. And for each process image, we compute a Laplacian pyramid. Then, we compute the output Laplacian pyramid by interpolating all those pyramids. And finally, the output image is computed by collapsing the output Laplacian pyramid. This allows a speedup of approximately 50 times on CPU and 20 times on GPU, compared to the approximation introduced in the original paper. This leads to a computational time below half a second per megapixel on CPU. This is fast enough for interactive image editing, and thus the local Laplacian filters are now used in several Adobe products with our new algorithm as an implementation. Let's now look at what those speed-up results mean concretely. Here is again a flower example, which details are enhanced with the local Laplacian filters. Here is the approximation we obtain using 20 reference values for the remapping function. We get an image on which we can see no visible differences. If we use 10 values, we can see small differences, but the image is still very satisfactory. Eventually, it breaks down, and we show in the paper that we can predict when using the bandwidths of the remapping function. Let's now move to our second key contribution, making the link between the local Laplacian filters and better-known filters, in particular the bilateral filter. Let's look at the equation for the bilateral filter. Its result is an average with a Gaussian spatial weight over of the input intensities weighted by a Gaussian over the intensities differences. This equation has a lot of similarities with the equations that we have obtained for the one-level local Laplacian filters. It had also a spatial Gaussian weight that came from the Laplacian pyramid, and the remapping function was depending on the intensity differences. We can make this equation even more similar if we define a remapping function with a Gaussian. Even if this function is different from the one introduced in the original paper, which was defined by power functions, it is very similar. And it gives visually very similar results, as you can see here. The equations are still difficult to compare because of this term, IP, in the equation of the one-level local Laplacian pyramid. However, one can rewrite the bilateral filter to get a more similar form. Indeed, since the sum in the bilateral filter is normalized, one can add and remove the image value to make the bilateral filter appear as a perturbation over the image. Now, we have very similar equations for both filters. Both appear as a perturbation over the initial image. Both have a similar spatial weight, and the intensities of the neighbor pixels have a similar influence. The major difference that remains is that the bilateral filter sum is normalized, and not the one of the one-level local Laplacian filter. That has an important influence, especially on edges, and I encourage you to look at the paper for a more detailed analysis on this point. There is also another major difference between the bilateral filter and the local Laplacian filter that I have discarded for the moment. The local Laplacian filters are multiscale. So let's look at what this multiscale aspect means visually. So here is an input image. And here is the same image with the detail enhanced only by the first level of the local Laplacian filters. You can see that only the very fine scale details are increased. If you add the second level in the local Laplacian filters, we obtain this image. And here we go until 4 levels. You can see that gradually more scales are increased. And if you go until 8 levels, which is almost the full local Laplacian filter, you can obtain this image, which increases the image content at all scales. Now that we understand better the local Laplacian filters, I will explain to you how we can use them to perform style transfer. For that, you can think of local Laplacian filters as remapping of pixel differences. Let's begin by looking what the simplified one-level local Laplacian filter does to a pixel P, in the ideal case where it has a single neighbor, Q, with which it has an intensity difference, IP minus IQ. What it does is that it changes it into a value, OP, which has an intensity difference, H from IP minus IQ with IQ. We show in the paper that H is a function that has a very simple relationship with the remapping function used for the local Laplacian filter. I encourage you to look to read the paper for more detail about it. The question is now, what happens in the real case, where there are several neighbors? In this case, all neighbors influence the value of the intensity of the pixel P towards their target value, defined by the function H. And the resulting output value is an average of all those target values. So in fact, in this one-level local Laplacian filter, H controls how the gradients are changed from the original value, IP minus IQ, to H from IP minus IQ. That gives the idea of using the histogram transfer function between gradient histogram in an input image and a model image to define the positive part of H. Since we need to define H for negative value as well, we mirror it so that we treat positive and negative gradients the same way. Now, by defining this single function, we can define the local Laplacian filter that will perform style transfer. And here are some results. Let's look at a well-known photograph that we take as a model style. We can compute its gradient distribution shown here. And here is an HDR photograph to which we would like to transfer a similar style. Since it is HDR, its gradients are in a completely different range than the model photograph. If we now use the two gradient histograms to define the transfer function, we obtain this function that corresponds to an intuition since it compresses the intensity values. Applying the local Laplacian filters with this function, you obtain these results. Notice the horizontal axes in the histograms have changed, and the histograms are now in a similar range. The images also have a very similar style, and there is just some fine-tuning to do. Repeating the process leads to these results. Visually, that's only small changes, but if you look at the gradient histograms, they are now almost exactly the same. Here are some results in higher resolution. Here is our input image, And here's the results when transferring the style of the image in the top right corner. Here's the same input image, but with a different model, which has strong gradients and a high level of details everywhere. And here's the same model as before. Here's the same model again, but this time with a different input. I encourage you to look at the paper, where you can find a lot more analysis and results. To conclude, I have shown how to speed up the local Laplacian filters to make them fast enough for interactive image editing. I have shown how they relate to the bilateral filter, and I have explained how they can be used to transfer the gradient statistics from one image to another, performing photographic style transfer. You can find the MATLAB code for the fast local Laplacian filter on the style transfer algorithm on our project webpage. Before finishing, we would like to thank the people who have helped us. Thanks for your attention.
Okay, we have time for a question or two. Please come up to the microphones. I'll ask one. Can you comment on the relationship to the previous paper? So they tried to work on removing textures or blurring textures while preserving edges. Could your method be used to do the same thing?
No, our method will basically not remove texture. It could enhance it, but that's one of the limitations of the method. So other people have shown that the local Laplacian filters are not really as good as other methods to suppress details because of this weight I have mentioned. But on the contrary, it is very good at increasing texture, so it will increase the texture very well.
Okay. The next speaker can go ahead and set up. And I see one question in the back, but the next speaker can go ahead and come up. Go ahead.
Hi, Andrew Adams from Google. I'm a huge fan of the technique.
Thanks.
I think your timing numbers are a little pessimistic, though. I've found on my laptop a well-vectorized parallelized implementation is more like 60 milliseconds per pixel, and on my desktop it's more like 15 milliseconds per megapixel.
Thanks a lot, I guess. It's a very nice comment.
So is your number just single-threaded scalar C? Where did the 350 millisecond number come from?
So it was on a single CPU. And maybe the method was not completely optimized. So.
Okay, let's thank the speaker.